Welcome back to module 5. So far what we have discussed, we have shown general properties of time evolution operator, and we have shown that because it is unitary operator, its time, its norm is preserved. That is why normalization constant does not change over the time during the time evolution of this system. Next, we will go over the numerical implementation and what are the complications associated with the numerical implementation. So, what we have shown so far is that mathematical strategy to obtain solution to the time dependence Schrodinger equation. Time dependence Schrodinger equation So, this solution to the TDSE can be very easily obtained by taking this form time evolution operator e to the power minus I h t by h cut psi x 0. We can obtain that, and then we have seen that this procedure to find out this mathematical solution was very simple and it is very straightforward. But its numerical implementation is not an easy task, and we will reveal why it is not an easy task. So, I have e to the power minus I h cap t by h cut, then I have psi x 0, and this is the part we have to numerically implement. As the time evolution operator is an exponential operator, its numerical implementation requires some method of calculating the matrix exponential. So, one of the procedures which we have already seen in Python tutorial 2, that we can represent a wave function, this kind of wave function under grid representation, and we know how to represent a wave function on a grid. And the moment we represent a wave function on a grid, we have to find out how to represent this operator on the grid. And in order to get that idea, we have already mentioned that this operator will be expressed in terms of matrix on the grid, and if this is a matrix, then ultimately we have to find out, in order to find out this operator, we have to find out matrix exponential, because H is a matrix in the grid representation. Almost all currently prevailing numerical methods which is used to solve TDSE make use of grid representation of a continuous wave function that we have seen. So, grid representation, it means that the problem domain, if this is called problem domain, which means the position space, this is called position space. This position space is divided into uniform grids. And this is something which we have already understood in Python chapter, in Python tutorial 2. We have shown how to represent the wave function on a grid. So, basically we have to take some kind of x minimum and some kind of x maximum, and this range will be divided into small interval, and each point is going to be the grid. So, this is called x grid. So, because I have the x coordinate here as a position space, we are using we are dividing the entire x coordinate into very small interval. And if we do that, then if I have a wave function, let us say something like this, this is your wave function. This kind of wave function, let us say at equals 0 time. I have this wave function x 0, then I will be able to write down this psi x 0 0. So, when I say x 0, it means that this one is x 0, then next one is x 1, so on like this way, and this is going to be x n minus 1 if I have n number of grid points. So, if I have so then function value at x naught, these are all for t equals 0, is going to be, let us say y 0, then x 1 is going to be y 1, x psi x 2, that is going to be y 2, and so on like this way. So, then in the end I get x n minus 1, that is going to be y n minus 1. So, these are the discrete values we get. So, basically what we are doing, a continuous wave function which is supposed to be continuous, but on the grid we are discretizing the wave function. And this discretized wave function can be very conveniently represented as a column matrix that we have seen. So, the initial wave function will be represented as a column matrix like this, that is going to be y 0, y 1, y 2, y n minus 1, a column matrix. And the moment we represent the column matrix here, so this part has been represented by this column matrix. Question is, how do I represent this exponential operator in terms of a matrix? Because in the end, if I multiply this matrix by the wave function, I get back the wave function at a particular time, and that is the motivation of doing this exercise. What would be the matrix representation of this exponential operator? Now, there are problems and there are solutions to it. The first problem is that finding an efficient and accurate technique of calculating the matrix exponential has been an open problem for many decades. What do I mean? It is not an easy task to find out if A is a matrix and A operator is represented by a matrix, let us say, then exponential of that matrix is not an easy task to find out this exponential. But there is a quick solution. The method of getting exponential of a matrix is heavily simplified if the matrix is diagonal. So, if A is a diagonal matrix, which means that I have values A 1 1 0 0 like this, sorry, this is going to be 0, then A 1 2 0 0 0 A 1 3 like this way, only diagonal elements are present. Let us say this is some values, let us say A in n, this is going to be A 2 2, this is going to be A 3 3. So, if I have only diagonal element present in a square matrix, then it is called a diagonal matrix. And if I have a diagonal matrix, then e to the power a exponential of that matrix can be calculated as by exponentiating each diagonal element as follows. It is going to be e to the power a 1 1 0 0 0 0 e to the power a 2 2 0 0, then 0 0 e to the power a 3 3 like this. So, if A is diagonal, then exponential of that matrix can be obtained by exponentiating each diagonal element. This is not true for any matrix, it is true only for diagonal matrix. So, what is our task? Our task could be, if we would like to use this trick, this simple solution to get the, so our unitary operator, what is the time evolution operator is following. This is the time evolution operator, and we have to find out the matrix representation of this time evolution operator. What we need to do is that we have to convert this to be a diagonal form, in a diagonal form. The moment we get that, then we will be able to use this trick to get the time evolution operator. So, that is going to be our target, but the target cannot be, this is problem 1, solution 1, but the target cannot be solved, the target cannot be achieved very quickly. It is because this Hamiltonian operator, I will show why it is difficult, because the requirement for using this technique, we have to use, we have to get the Hamiltonian operator in the diagonal form. So, and in order to get the Hamiltonian diagonal form, it is not an easy task, we need to use different tricks to use that. We all know that Hamiltonian is a sum of kinetic energy and potential energy terms. So, we have to individually check whether so problem number 2, is that as the time evolution operator contains Hamiltonian operator e to the power minus I, and this is Hamiltonian operator. Hamiltonian operator is nothing but the summation of kinetic energy part, which is given for single particle one dimensional problem. Still we are dealing with single particle one dimensional problem, plus Vx, that is the Hamiltonian we have, which means I have kinetic energy operator plus potential energy operator. There are two operators which are clubbed together to form this Hamiltonian operator. And we are still assuming that Vx is time independent. We will come to the problem later where we will be dealing with time dependent V. So, because this is a summation of these two operators, so one can write down here e to the power as like this, t plus v t by h cut, which is, we may want to write down like this way. This is nothing but e to the power minus I t by h cut e to the power minus I v t by h cut. We may assume that this is true, but this is absolutely not true. We cannot write it like this way. So, we cannot separate these two operators as a product of individual operators like this. This is not true, just because t and v, they do not commute. T and v, these two operators generally they do not commute. And because they do not commute, we cannot write down. Why? I'll explain it very soon. But there is a solution. Solution is that approximately one can express the time evolution operator as a product of kinetic and potential factors after discretizing the entire time interval. So, two comments I have already made. I will prove it very soon. First comment is that this is not true. Always they are not equal. They are always, they are not always equal, because these two operators do not commute. And the solution can come approximately, one can express the time evolution operator as a product of kinetic and potential factors by discretizing the entire time interval. Let us say the time interval for which we are looking at the dynamics of the quantum system is 0 to t. It is starting at t equals 0 and it is ending at t equals t time, at any time t. But this interval has to be discretized by very short time step delta t. If I do that, So, if I do that, which means that I have a time starting at t equals 0, ending at t, that is the max, and each time step is discretized now and time interval is delta t. If we do that, then I can approximately write e to the power minus I age. Now I have delta t, very small time step. For very small time step, I can approximately write they are equal. E to the power minus I t delta t by h cut multiplied with the power minus I v delta t by h cut. This is just an approximation, and we are splitting these operators. That's why it is called split operator method. This is called split operator method. So, we have to now prove, first of all, we have to show that this is true, this inequality is true, and then if I consider very small time step in the time evolution, then this equality may hold. I have to first prove this one, then I have to go for a proof for this one. So, we will move on and we will see how to prove this. So, let us look at the split operator with discretized time. So, we here what we will do, we will elaborate the argument which we have given that we can split we can use the split operator approach. The split operator approach we can use if I am discretizing the entire time interval, and the way we can do that is following. Let us say psi x 0 plus delta t. I would like to find out this wave function. That is going to be the unitary operator, which is the time evolution operator for delta t, then psi x 0, which is nothing but e to the power minus I h cap delta t by h cut, then psi x 0. And once I know this function, then I can find out x psi x 0 plus 2 delta t. So, at this point I have been able to get the wave function, that is the initial wave function. Then at this point I have the wave function which is x delta t. At this point now I have x 2 delta t, and like this way I am just propagating the wave function. The wave function was initially was here, then it is like this, then it is like this, and so on. It will keep propagating in time, and that is what we are writing here. So, this is going to be e to the power minus I h delta t by h cut. Then here I will write down x 0 plus delta t. This has become now initial wave function for this propagation, next step propagation for the next step. Similarly, I will be able to write down x 0 plus 3 delta t as e to the power minus I psi. In this case now, this part, this wave function would be my initial wave function for the third step propagation, which is going to be x 0 plus 2 delta t, and so on. Like this way we can propagate. The final step, let us say, is going to be x 0 plus n delta t, n number of steps I have gone in the time frame, and that is going to be nothing but e to the power minus I delta t by h cut, then psi, this is going to be x, 0 plus, remember I need the wave function just before this, which means it is going to be n minus 1 delta t, and that is the way we can get this. So, this is nothing but, so t, total time t max, that is maximum time I am going there, that is nothing but initial time plus, so this is going to be initial time plus n multiplied by delta t. So, n times we are doing. So, collectively this entire set of time evolution, discretized time evolutions can be written as like this: psi x t for the wave function at a particular time t is nothing but product of this e to the power minus I h t by h cut, then e to the power minus I h t by h cut. How many times I am doing the product? N times. So, n times I have to make a product of this discretized, sorry, this is not t, this is delta t, because already we have said that under this delta t approximation it will work. So, n times, and then I have to multiply by the initial wave function. So, that is the basic idea. So, finally, I am getting a way out for split operator method. I can use the split operator method where I will be writing e to the power minus I h t by h cut. The split operator, under the split operator method, what I am going to write here is that it is going to be e to the power is nothing but the product, n times product of this short time propagator, e to the power minus I n times. Then I can use this split operator approach. Split operator approach, what does it mean? I have already mentioned that I will be able to write down b equals e to the power a e to the power b. In simple algebra we do this very frequently, but when a and b are operator we cannot directly use that, but we can use it under split operator approach within this approximation, that it has to be divided into many short time propagator. So, question is what about the Hamiltonian operator? Hamiltonian operator, if we consider Hamiltonian operator, we will be able to show here. I have now e to the power, the requirement is that I should be able to write down this. So, I will be able to go write down this as a split operator e to the power minus I t delta t by h cut multiplied e to the power minus I v delta t by h cut, and we will just prove that in general this does not work unless delta t is very small, and this is what we are going to prove it first. So, first let us prove this one, that what will happen if I split it directly. If we split it directly, I have two operators, let us say a and b. I will be able to write down a plus b is nothing but 1 plus a plus b plus half a plus b whole square like this, which is nothing but 1 plus a plus b plus a square plus b square by 2 plus ab by 2 plus ba by 2 and so on. So, this is the form of e to the power a plus b. On the other hand, I would like to check what is the form of a and what is the form of the product of this exponential of this individual operators. So, that is nothing but I have to expand each one as Taylor series expansion. So, I will do it 1 plus a plus a square by 2 like this. Another one is going to be 1 plus b plus b square by 2 plus like this, and we have to get the product of it, and if I get the product, what I get, a 1 plus a plus b plus a square plus b square by 2 plus I have a b. So, what we see here already, there is a mismatch between the terms. We have been able to reproduce this part, but then this part is now mismatching. So, it is quite clear that as long as a and b non-commuting operators the definition of commutators of a pair of operators, we have shown that in the previous module. So, we are using that definition. So, if a and b are non-commutating operator, non-commuting operator, then we cannot write down this equality. They are actually unequal, they are not equal, and that is the reason why we cannot directly write down e to the power minus I Hamiltonian operator t by h cut e to the power minus t e to the power minus v. So, this is they are not equal. However, we have shown that if delta t is very small, then approximately one can write down e to the power minus I delta t by h cut equals e to the power minus I t delta t by h cut multiplied e to the power minus I v delta t by h cut. This is called split operator, and if we do that, this is definitely an approximation, then the error in this approximation, error would be proportional to delta t square. So, as long as delta t is small, the error would be small, and that we are going to prove right now, that if we express this split operator approach, then the error is going to be delta t square. So, for that we will start with e to the power minus I t plus v delta t by h cut, that is written as 1 plus minus I t plus v delta t by h cut plus minus I square by 2 t plus v square delta t square by h cut square plus so on. We just reorganize little bit, plus minus I t plus v delta t by h cut plus minus I whole square by 2. This is going to be t square plus v square plus tv plus vt delta t square by h cut square and so on. On the other hand, if I try to express this product form, e to the power minus I v delta t by h cut, then I will be able to write down 1 plus minus I t delta t by h cut plus minus I square by 2 delta t square t square, then delta t square by h cut square, like this. This is one term, and second term is going to be again 1 plus minus I v delta t by h cut plus minus I square by 2 v square, then delta t square by h cut square, and other terms are there. So, if I explicitly make a product of this, then what I get? I get 1 plus minus I multiplied by t plus v plus minus I square divided by 2 t square plus v square, then delta t square by h cut square, then minus t v delta t square by h cut square. So, in order to find out the error, if I make a subtraction between these two, then what would be the error? I will find out the error by subtracting these two expressions. So, I will be able to get e to the power minus I t plus v delta t by h cut minus e to the power minus I t delta t by h cut into to the power minus I v delta t by h cut. So, that is the difference I take. If I take the difference, then in the end what I will get, this part will be cancelling out, this part will cancel out, these two parts will cancel out. So, I will have the difference between the remaining parts, and difference between remaining parts is going to be, one can show it very easily, minus half little bit of simple algebra, one can get this t v minus v t by 2 multiplied by delta t square by h cut square plus other terms. But remember, other terms will have delta t cube term, delta t fourth term, all these terms. So, what we will do, we will take because delta t is already very small, we have considered, in that case we can neglect all other higher terms, and we can say that the error, if I do that, then error is going to be proportional to delta t square. So, this approximation, that e to the power minus I h delta t by h cut is going to be e to the power minus I t delta t by h cut into e to the power minus I v delta t by h cut. This approximation will give me an error of which is proportional to delta t square. So, as long as delta t is very small, we will be able to neglect this error, and we can write down this the split operator part. This error which we have mentioned in the split operator approach can further be reduced. So, error can reduced, and it will be then proportional to delta t cube if we take this symmetrized product of the split operator method, which means that e to the power I t plus v delta t by h cut, if we take this form, which is e to the power minus I t by 2 delta t by h cut, then e to the power minus I v delta t by h cut, then e to the power minus I t by 2 delta t by h cut. This is a symmetrized product. Why it is symmetrized product? We see that here I have kinetic energy part, here I have kinetic energy part, here I have potential energy part. If I take this kind of product, the symmetrized product, then error, one can use the same technique through Taylor series expansion. One can prove that then if I do that, then error would be proportional to delta t square. This is delta t cube. So, this is better approximation, because if I take delta t to be very small, then error would be much smaller here than this one. And we will show the numerical implementation of time propagator with this symmetrized product in the next session.